Hello everyone, welcome to the last standard lecture in the casing design session of the course. This is lecture number 5, part 1. I have to say to you a little bit about the previous session. We talked about API collapse amongst others, and as you may remember, there were a few slides missing there. They have been added, and I also made a video that I think most of you guys got a link to, so that you could see the full connection between, the steps on how to deduct collapse resistance for API collapse. Now, we will briefly touch upon it today too in repetition, going through the standards, because standards, they describe how to do it. And also I was a little bit holding back on the analyzing the results. That is also something that comes as part of the standards, more or less. You can put it one way or another. The methods are described in the standards, and the thing about it is the significance of the methods are as important as the methods themselves, meaning understanding what they do and how to apply this knowledge. Today we have quite a comprehensive slide pack. I think there's like 86 slides left. Dividing that on the number of minutes, it's almost going to be a movie, I guess. But we will not cover basically field development if time is short. And we may touch some of these slides very, very briefly, as they are kind of repetition, as said. Standards describes the method, which we have been talking about earlier. So we may not need to go into too much detail per slide. We have been quite good at that earlier in this class, I guess. Yeah. Also, what I'm thinking of, we are going to have a theoretical exercise. That one was sent on email to you guys, and yay, I got my access to the NTNU system just after midnight. So yeah, that means, for one thing, we can start to communicate properly, and I can use Blackboard again. What the teaching material in this class will be is that 80–90% finished compendium. Again, that is like a comprehensive pack for you to bring as luggage on and read through and know where to find information about stuff later on. And in preparation for your exam, of course, all the equations are discussed, and some of them are even derived there. And also the exercise, I think, will be submitted there. Next week I'm completely busy, so I cannot help you next week. What you can do, email me your questions. You're not a too big class. What I propose is that you guys just make a small session for yourself and help each other on Tuesday, because there is no student assistant here. And if you have questions, just bring them over to me. Make a voice thing sent over, or just pictures of we can't solve this and we can't solve that, or we need more information, whatever. Basically, I don't think that you have too many questions. Did anyone look at the exercise? Did everybody get it? Yeah? So I sent it out, I think Tuesday evening, if I'm not mistaken. Yep. So I may not have everyone's email address since I don't have haven't had access until now. Anyways, I think that we will not be too strict on the submission deadline. Maybe the week after, at the end or something like that. We will keep talking by mail, I think, and find out what is a good time. I have a gut feeling that not next week, but the week after, what we can do, we can try to make half a day into this in the dungeons. in the basement, they have now set up the computers with the landmark software. Moved from our beautiful office in the fourth floor we used to have just above the cantina of the employees here. Huge, nice room with the best ventilation in the whole building. It was so popular to sit there and work just for the students. Now it's used for something else, unfortunately. We will go in there and we will do that exercise, practical exercise, and do like a one section casing design, just so that you guys get an idea about how this is set up. And not only does that tell you how what we're going to do to complete this class, but it will tie into some of the details that we're going through here. It will just show you that here are some regulations for casing design and what they really mean. We can talk about them more in detail in that session. What the practical meaning of them are from different angles. That's kind of important. But there's no time for it right now. Also, we can discuss the theoretical exercise that it's compulsory, I guess, for your exam that you need to submit so many exercises, I guess. And yeah, we will bring up that one and put in the deadline also, I think, in that practical exercise. That's a plan. If you guys have input, let me know and we'll sort. What is left for us? Regulations, the standards for manufacturing, and also for the strength of pipe or how we calculate. We have gone through the calculations in brief now. We're going to talk about casing wear. And the slides that you'll see there is from one of the students, basically, in that class that we talked about, autumn class that used to be here. And then we'll talk a little bit about modern calculation techniques, and if there's time left, we can talk about well field development. That part is something that will give you more value if we talk through it. Between us, and you guys can ask questions, but you will get value also just from reading it, and that you can do by yourself, and it will not have any significance for this class and your exam, but for you as engineers, I guess, that you have broader luggage. You will learn this later on anyways, once employed. Well, all you guys are probably already employed, I guess. If not, that's happening imminent. All right. Let's move to this is the overview of chapter 3, casing design process, design analysis. We are baking that into a few sub activities in the different other chapters, so we're skipping straight to the regulations. And here you'll see an overview of to the right, typically international. Every country would have their own regulations, even if they are not doing oil and gas. So few small countries, they don't have oil and gas, and they are discovering oil and gas. They would have something in the mining and something else they relate to, and then they establish something. In Norway, it's kind of special. I've been studying the legislation in France. They do not do the same approach. What we do in Norway is that we, the national, the PSA, the national authority, points a lot towards the NORSOC standard. It doesn't really frame very specific what to do, but they say, for example, such as, and then they point to a section in one of the NORSOC standards, which is again expanding more on the topic than and giving a minimum standard on how to do things. What comes below the standards, looking at it this way, with a Norwegian perspective, would be any company's standards and philosophy. And the regulations of companies would be more, call it firm, more detailed, and wider. So that's why this triangular shape is used. And in the end, at the bottom, you will have the specific engineering designs and your programs, detailed procedures, equipment procedures, which you typically get from service providers. And the casing design that you do as professionals would sort in that box. Then you go really into the details of every single thing. Every property is included. To the left is an expansion of corporate standards and philosophy. This is, you can find it on the link below, Equinor's structure for it. Yeah. And you'll see by reading this where the specifics are. There are so many levels. Up on top, you have the absolute requirements, functional requirements, what you absolutely need, and then what is valid for absolutely all activity. Under there comes requirements, technical requirements, and description of work process, how you do things. This is the best practice. Repeat this way of doing it. It gives you the least risk, the least exposure to damage of environment and personnel, equipment, so on. Yeah. Here comes more details about casing design regulations, and this is an extract from the governing documentation. All that I'm lecturing here now is from the governing documentation made by NTNU for that class that I've been advertising so much for. But you will find that this would be very, very like coming under the requirements part of governing documentation of more or less all major operators. Yeah. Casing design shall be performed for all wells by skilled personnel using industry recognized software. All components should be in the well barrier elements shall be designed to withstand the maximum load and stresses. And again, remember what would be the maximum load and stress in any situation for any well? The pressure test, yes. The pressure test is designed to exceed any of the natural occurring states. Formation properties should be checked and double checked for that matter. Kick tolerances should be in there. Recommendation would be a triaxial design, and that's fundamented in standards. We'll see that later on. Yeah, and there we go over to what is again a recommendation, and that's to do integrity checks with the FIT leak-off tests or extended leak-off tests. Now, just as a quick thing for you guys, what happens if your leak-off test or FIT shows that the shoe is weaker? The formation at the shoe is weaker. what significance does that have for you as a drilling engineer? You have drilled. Do you know how that works in principle? In principle, you have your old rat hole going down to here, and the casing is 1 to at the max 5 meters above the bottom, unless you have drilled with a hole opener type, right? Then you have a smaller rat hole that the casing most likely doesn't fit into, right? So 1 to 5 meter rat hole, that one would have poor cement quality below, right? Because the cement, when you pump it, it goes up. So below here you might have some mud filled cement. Very often rotten cement in the rat hole. So and the old hole, if we look at it like this, the old hole goes for the casing goes something like this, right? And you have to drill past and most likely 3 meters. That's what your regulations would be. Otherwise, you're not going to test in the rat hole, right? You don't want to do that. You want 3 meters new formation, okay? And then, and here's the point that I wanted to make to you guys. You take a leak-off test or an FIT, and your prognosis was 1.6. Sorry, I'll make the. And instead you find 1.55 SGs. That's the formation strength. What significance does that have? What do you immediately need to do? That could be the thing, yes, definitely. But if we are in the casing design class, what do we do? So on the board here, in the middle of the slide almost, kick tolerance, right? Kick tolerance. The kick tolerance, the FIT at the shoe and the formation strength there is very much, the kick tolerance is very much affected by the strength of the formation, the weakest part under the shoe. And kick tolerance again is a little bit, let me put the word weird, how the industry is doing it. Because what do? You only make a snapshot, right? Whereas the kick tolerance is a snapshot for every millimeter or every inch that you drill. Actually, there's a new snapshot, right? Whereas what you do and what is the practice is that you check it at TD, right? Be observant of that, guys. If ever you see a weird formation, a poor pressure plot, a hole stability plot with a weird pressure prognosis and fracture gradient setup, double check as you go down, because regulations will tell you, okay, it's okay that you just do it at TD, and still there's a whole lot of weird stuff going on. Let's say a formation, a sandy formation with that has been depleted for some reason or with some weird properties, right? Double check it. It's your ass. Yeah. Triaxial designs, yes. FIT leak-off tests and yeah, load cases, static and dynamic. When you are producing the well, when the well is shut in, for example. Let's face it, the real extreme forces, they are when the productional forces, not during drilling. During drilling, you have some torque and drag and maybe a kick and so on, but unless you really do something bad, what is the absolute worst case scenario in the drilling when you take a kick? It's when you have a bubble that comes in, a gas bubble here, and you don't bleed off. What happens with that gas bubble? Let's say that the pressure here is 300 bar. What's going to happen? with that gas bubble. Let's say that you have a gas bubble of 2 cubic meters. That's what it wants to do. What happens if you don't bleed off at the top? It doesn't expand, right? And what happens then? It keeps the pressure. So it's going to have 300 bars going here, like this. And it goes up to the top, right? So your mud profile, let's say that you have 1.5 mud, it's going to look like this. After the gas bubble has come to the top, you have to move to 300 bar, and you have to do this. That's the absolute worst case, right? So sleeping on the job is not a good idea. Just keep it shut in and forget about the well. Yeah. Yeah, not a good idea. All right. This plot is kind of important and it's part of your exercise. This one shows you the difference between the grandmother, like I told you. The grumpy grandmother is called Velcat, and the neat and easy one is called Stress Check. And you see the difference between them there. The Velcat takes in account your exact temperature, meaning as good as the software can model temperature. Whereas Stress Check does the simplification and say, no, there's no change from the reservoir temperature. What is your reservoir temperature is what we're going to calculate with all the way on top. There are more differences than that between Velcat and Stress Check. Velcat models wellhead growth, the thermal expansion of the steel coming up, the wells trying to come up. It models packer forces on tubings. It models several other things too. And you can set up very, very special cases, like a plug in a well and see what happens with the leak above and below, and so many special custom loads. And you can model, that's kind of cool. Velcat is actually a regulation that many set as a requirement from you see design category 2. If you have the condition that the well is more than 10,000 psi and 150 degrees Celsius, then definitely Velcat is your case. One of the things that the Velcat does is to model annular fluid expansion. Annular fluid expansion, AFE, not to be mixed up with acceptance for expenditure, which is your budget for a well. Annular fluid expansion means that the same mechanism as we are having here, gas migrating, and that's another dangerous mechanism that we have been talking about, right? That gas from the formation migrates up in your annually, and all subsea systems have absolutely no surveillance by standard delivery in their B annually. So your casing design for a subsea well has to be checked in Velcat, regardless, to find annular fluid expansion in the B annulus, right? When you start to produce, you're going to heat up your B annulus. Whatever fluid's there, it's going to follow that rule of thumb that I talked about, 1 bar per degree, right? So you have the difference here between the real produced temperature and whatever it was your base case was. The base case is the fundament for every thermal stress induced in the well. We call it yeah, the base case. It's not called base case. It has a specific name and I've forgotten it. It's it base case. You understand what it is and you will recognize it when you see the name of it in the softwares. Whatever your starting point is, from there on you will have geothermal stresses. Why? Because casing always, more or less, are hung off in the top, and not only hung off, we saw that it's locked. It's not allowed to come up. Regardless of what forces and whatever you do, it's locked into the wellhead. And in addition, cemented in the bottom. It means that it's stuck in both ends, which means that if you heat it up, the expansion, the natural expansion of the steel is going to be manifested as a stress. Whatever you had in your base case, imagine I forgot that name. The stresses will be added, right? Yeah. And your exercise has one calculation using this, and the simplified version of the temperature that we talked about earlier.
The casing is not isolated with the cement. Why is so important to have this in configuration for the internal casing?
The temperature immune.
Yeah, the
Yep. A railroad, when you are during winter, you'll see that the gap between the rails is quite big. During summer, they are almost together. A bridge always have something at the at both ends. It does this. According to the temperature. When it's cold, it contracts. When it's warm, it expands. Even concrete does this. Yeah, the steel is actually very much, call it alive temperature wise. You heat it up, it gets longer. Okay, so a steel rod, and the well will do that too. As I said, when you start producing, you'll find that the temperature in the well that was like this, the geothermal gradient, right? You have maybe 10 degrees in the steel at the top, in your tubing and so on. When you start producing the fluid at 100 degrees or 150 or whatever it is, the temperature is going to rise like this. So in the top you now have a temperature increase of 50 to 100 degrees. Increase. You have heated up your steel, your whole well, with 50 to 100 degrees Celsius, right? It means that the steel that is in your casing, fixed at the top, fixed at the bottom, trying to expand, it cannot. What does it do? It leaves a stress inside, an additional thermal stress.
Yeah, I mean, what I would like to know is that, yeah, maybe give your case of production is the production tubing. Is it in the problem that is it the casing that submit to that temperature?
All of them. Absolutely all of them. What we need to do and what makes it so advanced, the temperature modeling, like I told you, it's like a sandwich. You have first the fluid from the reservoir giving off its energy, the heat, to the tubing. Then whatever is in the annulus, very often in the A annulus, there's a brine. Then that one gives off, takes a heat and gives it off to the next casing, your production casing. Okay, outside the production casing, let's say it's a cement. Then you have to calculate, and there are three mechanisms going on. That's what we talked about the last time, right? Three mechanisms. Yeah, yeah. I actually made a temperature model once, and it's it's complex. The best temperature model I've ever seen belongs to IFE, Institute for Energy something, up here. If you look into the more modern call it well planning tools, engineering tools. Oleasoft in Oslo, they are one of the more modern ones. They are using the IFE temperature model. What is kind of cool, I told you guys about the fiber optics that you install in wells, and you see pressure, temperature, and you can even listen to the well for every meter along the casing. Now, the temperature modeling that IFE has, and it was tested on one of these wells because you can measure the temperature for every meter. It is definitely the most accurate one that I've seen, the IFE temperature model. It's fabulous. Temperature modeling. If you want to program the crap out of your master thesis, then try making a temperature model. Yeah. All right. We will talk more about the temperatures, and thank you for the question. Please ask anything, guys. Basis for well design. These are the questions that you need to ask before you start developing them, right? What is the well going to be used for? Is it a producer? What is it going to produce? Is it going to be a water alternating gas injector? Is it going to be converted to an injector later on? Blah blah blah. Is it going to be fracked? Blah blah blah. I mean, how long is it going to produce for? And what is going to be the abandonment? Is it going to be a slot recovery? Like you're going to drill to a new target? How many times are you going to reuse, for example, the 13th rate to reach another target and produce? So all these things you need to ask before you even touch your computer, as per se. And here comes the part that I'm thinking that we should go more into depth with. It will give you meaning to you guys just reading it, but what they actually mean, every single point, we can discuss more in that lab exercise in the dungeons. Design factors, we have talked about them. They are definitely going to be very much mentioned by any governing documentation for casing design. Dogleg severity override. You guys have an idea what this is? What is a dogleg severity override in casing design? It means that if you plan a dogleg, say vertical top holes, it says plus 5.5 degrees. Okay, so whatever you do in your calculation is that it's gonna calculate with a small deviation, right? Because you never drill a straight hole, do you? And it's the same for more deviated ones, and you add curvature to any calculation that you do, it increases the bending stress, if you see what I mean. It gives you an addition. You need that because the casing would not be straight, and even if you underestimated the dogleg, you have something to go on here. Yeah. Kill margin, we talked about it. This is again just reading material for you guys. You are competent readers, most of you. Connections, premium connections were required. This is just a reflection. Your company will give you your specifics. This is what we set up for NTNU. Kick tolerance regulations. Again, this is something that you will see in, for example, Norfolk D10. We talked about why it's 8 cubic meters for a 12.25 inch. Casing wear. I don't agree to what I wrote here. It says one of the two scenarios. I'd say that you need to have an idea about both, not or, but both. You need to know simulate the wall thickness loss, and you need to know well, it's not just straightforward. You actually for any casing, just simulating that okay, I'm going to drill this section. What is the wear? It's not going to work. What if at the more or less the end of that section you get stuck? You have to cement back and you have to re-drill it, right? So you always need backup. So the first question is going to happen in a situation like this. Everybody's going to turn around, look at the drilling engineer and say, can we drill again out from this 1338 or 958 or whatever it is, 20 inch, right? So in this case, I'd say plan for backup. And you don't need to see that, okay, my curve allows me to drill this, and still there's a little bit. It needs to be checked for double the activity that you think it's going to be, at least. Yeah, load cases, mandatory design load cases. There's a set, and the table that we made at NTNU governing documentation, you have seen it for drilling operations and for production in one of the first sessions, and we have discussed in detail the displacement to gas and tubing leak, this one. And design analysis requires that I say something. This is the pressure. This would be collapse. From here, it would be a burst pressure. This is the depth, and we see a well here for reference. So at the wellhead, the Christmas tree, of course, there is a shut-in. The blue line being the external pressure of the tubing, and it would be 0 at the tubing hanger. It would be the gradient of the packer fluid going down. The pressure inside the tubing is this stable one here. It's a natural pressure from the reservoir, and you deduct the density, the weight of the fluid that you're producing. Then you arrive at this point, and then you see the differential pressure is like this. If you get a leak very high in your tubing, the external pressure is going to move from 0 up until the internal pressure of the produced fluid, and it goes out like this with the gravity of the packer fluid instead on the outside of the tubing. So it's a collapse force and quite a significant load on top of the packer, because below the packer you will have this pressure, and the differential pressure now looks like this. A lot more differential. So this is what we call a collapse pressure for the tubing, and the highest one that can occur in the lifetime of the well normally. You have to of course check, is this a gas? Is it going to be produced water later on, water breakthrough, whatever density that water has, you need to check it. And there's another consideration. If I say production casing, what will you then think and respond? Suddenly, with a tubing leak, you will have quite a significant burst load on the production casing, right? So the tubing leak leads to all the stresses that the tubing normally sees will be transferred to the production casing, but the production casing has its own properties, right? It has a different annular fluid. It has its cement in a different spot. It has a packer set somewhere. So this case needs to be investigated for the production casing. Yeah. standards for pipe. There are two of them. I mentioned that the last time. Oh well, let me give you 2 seconds to ask questions. Two standards. One is for manufacturing that we will cover here. We have also talked a lot about NORSOK, and we will use NORSOK a little bit later on. We will just briefly touch the specification for manufacturing of casing, the API 5CT and ISO 11960. We'll spend a little bit more time on the calculation parts, the API 5C3 and 10400. Yeah, go ahead. Good question. I think they would touch upon things, but I have not seen anything, not in these two categories, if you see what I mean. Yeah, they would have things that would touch upon and be relevant, I presume, but not for these areas. They are not often used. Yeah. This is how they how it looks. They are basically the same API and ISO. Not much difference. So some argue that, but from your perspective, I'd say that no, they are basically the same. And the specification of manufacturing. You remember the process of manufacturing pipe? We went through it and all the different work methods as an example of what it is. And API specifies you should not have, or specifies, it specifies a recommendation. You can do whatever you feel like, but what you can do if you follow this is say that we have API quality pipe, right? Now, as I said, many are now no longer manufacturing API quality pipe because the standards are a lot less accurate when it comes to pipe properties. Say this chord height of 0.2%, probably many of them are much better than 0.2% today as standard without any problems, right? So this is just an example, but you'll find that many of them say that this is special pipe, whereas special today is the standard. That's my understanding of it. They are, for example, on wall thickness. We'll see later on in this PowerPoint pack that yeah that is much better than 12.5%. Yeah, and it specifies pressure testing after complete manufacturing and so on. Yeah. Yes, you guys need to. Why? Because the industry uses this calculation from Barlow that says 12.5% or 0.875 as a factor in front of the burst calculation, right? Yeah, my watch is there. First session ended.